from last homework sheet from last time that I handed out last time? Any questions about anything before we get going? Things going well? All right, so just to remind, we'll have a test on Tuesday. 4 questions on the test, as a matter of fact. Okay. We did cubic splines, so there'll be a question about verifying if a function is cubic spline or not. Like we'll go out on our homework. I will not ask you to find any cubic splines on this. Literally, can you check is something a cubic spline? You had your project over cubic spline, so that's why I'm not going to ask anything about creating another one. There'll be a question about least squares, so being able to use Excel to get your least squares model. There will be a question about Fourier series, being able to find a Fourier series in particular. I know that on your homework you've got some that asks you to figure out some series identities using Fourier series. That won't be on the exam. Literally, it'll just be using GeoGebra to create a Fourier series. And then Monte Carlo simulation, which we've already talked about today. Yes, you're right. Can I write that? Sure. Oh. So again, first one, verify whether a given function is a cubic spline. You had one like that on your homework over splines, right? Second one, we use your Excel to create a least squares model and define an R squared value. We both those things, right? I will have the data in an Excel file already for you, so you don't have to type it in. Okay, so I'll have that distributed to you, so you don't actually have to type it. Just have to know what to do with it. All right. Third one is create a Fourier series with GeoGebra. So we're going to have one more example like that now. I also want to do another one where we did the those series identities with Fourier series. I'm going to do another example, show you how those work. But again, the verifying a series identity using Fourier series is not going to be on there. Literally just creating Fourier series. Hey, that's an ugly looking water. And the last one's the Monte Carlo simulation stuff that we're going to start today after we do one more example of Fourier series. That'll be Tuesday's exam. It'll be 4 questions. And so you can't tell me what's on. You can't say I don't know what's on the exam. There you go. That's what's on the exam. All right. There's no final exam for this class. We'll have a final project instead. So I'll give you that last of your major assignments. Probably I'll sign that on Thursday so that you have it, which will mean that we won't have class next Thursday. I'll just have time in my office if you want to come by and stop by and ask questions about that. In particular, I'll be there. Okay. So we won't cover anything new on Thursday. Yes.
Is that going to be due at the end of finals week?
It'll be due probably Thursday of finals week. And I believe that was when our final was originally scheduled, was for that Thursday morning. So I was maybe on Thursday. We'll talk about that on Thursday. This coming Thursday. And that way you'll have a couple of weeks to get it done. I'm assuming you probably won't work on it while you're studying for the exam, but think about it a little bit, at least. But at least you'll have it ahead of time. And like I said, rather than having class on Thursday, the next Thursday, we'll use that for work time, and then you can come ask me questions if you've got questions. And why did that just go out? Why is this being so cranky today? What is going on with this thing? No. The mute button was on. I didn't touch the mute button. All right, anyway. Let's see if we can do one more example. Creating the Fourier series and then using that Fourier series to look at an identity. Ones we've already shown before, but just to give another example of how we work with that. So let's say the function that we're interested in creating the Fourier series for is x plus 1 between -1 and 0, and then 1 minus x between 0 and 1. And this again, one period. This is one period of the function given to you, so assume that it repeats. What does this graph look like? Let's start there. If we want to create this particular Fourier series, it'd be nice to know what it looks like to start with, right? Say that again.
It goes from 0 to 1 back to 0.
Yeah, so it goes up this way and then back down again here, right? And I'll just repeat that over and over again. So again, if we're thinking about when we look at the graph of the Fourier series here, we would anticipate that the Fourier series does a pretty good job on the straight line parts, not near the endpoints, but again, it'll have to round off at the endpoint. So it's going to have issues around the sharp corner, which we've talked about before. The boundaries are difficult to work with. That's why there's a whole series of volumes of textbooks dealing with trying to figure out boundary value problems. Boundaries are hard, generally speaking. All right, anyway, what do we do first? Yeah, integrate the function, right? So again, we want to integrate this in two pieces. I don't know why they decided they want to put all sorts of crap on the front of the room. It makes it difficult to walk around. All right, so first thing I want to do is integrate the function. Remember again, when you're in GeoGebra, first when you go to the website, make sure you go to the classic. And then second, make sure you've got your CAST selected, computer algebra system selected, and not the algebra system selected. The algebra system is just going to give you a number. We want this with variables in it, in particular with the n's in it for the sine and the cosine. All right, so first, integrate the function. The first part of it is x plus 1 from -1 to 0. The second part of it is 1 minus x from 0 to 1. We can type it in two pieces. Actually, we need to type it in two pieces to create the entire integral. There's our integral of our function overall. Could have actually just looked at so we had two triangles. That would actually have to integrate, right? Each of those triangles has an area of a half, so we need one. Remember, what do we have to do with this constant when we're done? Divide by the period, right? Period gets divided. So in this case, period is 2, so what'll actually be out in front of our Fourier series in this case will be 1/2. What do we do next? You're gonna get your A of n and your B of n, right? How do we find the A's? What are the A's the coefficients for? the cosines. We usually use the A for cosine, B for sine. Doesn't really matter with respect to GeoGebra as long as you know which one's which. Okay. So again, need to integrate the function times, what are we going to multiply x plus 1 by, and the 1 minus x by, and the other integral we'll do. What are we going to multiply by? It's going to be cosine of pi nx. Remember, the nx part comes from the fact that we're doing cosine of x, cosine of 2x, cosine of 3x, and so on. And the same thing with sine. Where's the pi come from? Why isn't we putting a pi in there? The period is 2 rather than 2 pi, so we got to put that coefficient in there to adjust for the period. All right, so I need to integrate this part from -1 to 0, and then do the same thing with the 1 minus x piece from 0 to 1. I can type. Need to add the two integrals together, right? Get the total integral here because we've got a piecewise defined function. Just notice I typed pi nx for one of them and then pi x for the other one. It doesn't matter, obviously, but all right, hit enter. We get that. Do our b's. Our b's are almost exactly the same, except that we replace cosine with sine, right? So it'll be the same exact syntax that we had in the previous part, except that we'll have sine rather than cosine in there. So again, we're adding the two integrals together because we have the piecewise defined function. We change the cosine to sine. Whether you did pi nx or n pi x doesn't matter. It'll give the same answer. I don't think GeoGebra cares if you have this x in there because it's going to assume the default is to integrate with respect to x unless you tell it something different. But since I've got two variables going on, I like to specify what the actual variable of integration is there. That's the only reason why I typed it in. By the way, before I even hit enter here, many of you may have already hit enter. Looking at the graph of the function, what would you expect this answer to be to start with? 0. Because what kind of, if I ignore, well, actually I don't have to ignore it. What kind of function do we have with regard to symmetry? It's even, right? It's symmetric about the y-axis. If it's symmetric about the y-axis, I expect an even function. Sine is an odd function, right? If it's going to be even, I'm going to have a series that's going to involve all even functions. It's going to involve the cosines, not the sines. So even before I hit enter here, I would anticipate that this is going to be 0. And it is. That okay? So far, so good? All right. All right. So to create our Fourier series now, say I call it F. First thing we're going to type in is the constant. What's the constant again? 1/2, right? So remember that we take the integral that we found on the first line and divide it by the total period, which in this case is 2, right? What goes in front of your sum? What do we have to divide the sum by, the actual series part? Half of the period, right? Remember, the half the period goes out in front of the sum, because that's the dot product, the inner product of the function with itself in this case is always a half of the period, the cosines and the sines. What is half the period in this case? 1, so there's not anything to divide by, okay? All right, so then our format for this is sum of We'll do the a of n's times cosine of n pi x again. If there were b of n's, then I would do plus b of n times sine of n pi x here. There aren't any b's, so I don't need to bother putting that piece in. And then just to get a graph here, let's say I do 10 terms to get a graph for that one. And let's turn off this other ones here so we don't see those. And scooch over. It looks pretty much like what we got. It's pretty cool. I like this stuff. Notice again that we said that just by looking at what the graph looks like and what we know about sines and cosines are continuous everywhere, differentiable everywhere, and sines and cosines are infinitely differentiable everywhere, right? So they're nice and smooth functions. That original function has sharp corners in it, so again, we would anticipate that near the corners, it's going to round off the corner rather than actually get into the corner, right? We can get closer and closer by taking more and more terms, but if I zoom in, I'm always going to see a rounded off piece there. You'll never see a point. Because again, sines and cosines are infinitely differentiable, so they're going to be infinitely smooth in a sense, right? No matter how far I zoom in, it's always going to have a nice smooth function piece, so it's never going to get into that corner. It's going to try, but it's never going to make an actual sharp corner there. Now, I should say it's never going to make a sharp corner because I'm cutting it off at some certain point. That process okay?
What did you get the one half?
Remember, for your constant, here's your constant here. This one always gets divided by the entire period. So this is so the period here is 2, so we divide it by the 2. So yeah, the constant that you get for the integral of the function is always divided by the entire period. The coefficient that goes out in front of your sum is 1 over half the period. In this case, half the period was 1, so I didn't bother typing anything. Okay.
Yeah. So for homework, you just want a screenshot.
Absolutely, just screenshot it. Yep. Screenshot, email to me. It's great. Yeah. As long as you do a screenshot that shows me what you've typed in here in case something's goofy. Yeah, but that's fine. Give me a screenshot of that and the picture. Maybe you have to do 2 of them, maybe, depending on how long the integral is, but yeah, screenshot's great. Yep. This okay? All right. So again, like I said, I want to do one more of these where we show an identity. I guess I'll do it here. Show an identity based on the Fourier series. So that requires us to do a little bit of more of analysis on what these terms are. As far as GeoGebra is concerned, it doesn't matter how goofy these terms get. It'll just go ahead and plug in the ends here, get your trig polynomial and plot it, right? But if we want to do something that actually involves an identity using your Fourier series, I got to get a little bit more of my hands dirty to figure out what these terms have to do. Okay? So in particular, I've got this cosine of n pi piece here. What does that do? 1 and negative 1, right? It'll alternate between 1 and negative 1, 1 and negative 1. So what does that make? Pardon me. So what does that make your numerator do?
0 and 4.
Yeah, it goes from 0 to 4, right? If this is negative 1, it makes a positive 2. Added to the 2, you get a positive 4. But if it's 1, then I get 2 minus 2, which makes it 0, correct? When this is 1, the numerator is 0, right? So which terms do we actually get? The odd terms or the even terms? The even terms, right? Because I put in 1 or 3 or 5. Oh, sorry. It's the even terms that are go away, right? Right? If I put in 2 or 4 or 6 or so on down the line, that makes that a 1 and I get a 0 on top. So the only terms that survive are the odd ones, correct? Okay. So if I were to write this Fourier series then by hand, I'd have a 1/2, and then you'd have the sum from n equals 1 to infinity. I only want the odd terms, so I would have 2n plus, let's do 2n minus 1 squared times your pi squared. And then you'd have cosine of 2n plus 1 pi times x, or minus 1. We only get the odd terms, right? One way to describe odd terms is to use either 2n plus 1 or 2n minus 1. Since I know the first term was okay, the n equal 1 term was okay, that's why I use 2n minus 1 here, because if I plug in 1 for n, I'll get a 1 for that first term. Trying to make it match. That part okay? All thrilled. Great. Fantastic. Okay. All right. So let's see if we can use this to get, again, like I said, another power series, not a power series, another series identity using the Fourier series ideas. So again, this should be equal as a series and as a function. It should be equal regardless of what I plug in for x, since everything here is continuous. If you've got something that has a jump in it, you have to be careful. But if I plug in something on the left-hand side, I plug in something on the right-hand side, I should get the same number either way, right? So in particular, let's start with plugging in 0. Why might I pick it 0? Well, what happens here if I put in 0 for x? It gets 1 all the time, right? So if I put in 0 for x, well, using the function, what value should we get out when we put in 0 for x? 1. On the right-hand side, we get 1/2. And then the series becomes, I can pull out the 1 over pi squared here. Oh, I forgot a number up top. That's not a 1 on top. I'll take care of it here in a second. That's not a 1 on top. What did we say the numerator was when it wasn't 0? 4. Yeah, that should be a 4 on top rather than a 1. So I can pull that 4 out in front too. I fixed it. Out of sight, out of mind. Now it says 4. All right. It's a 4 over pi squared, yeah. All right. So now I can solve for the series and get a series representation for something. So if I solve for the series, I would subtract 1/2 and multiply by pi squared over 4, right? So at the end, we would get that the series from 1 to infinity of 1 over 2n minus 1 squared is pi squared over 8. Right? Because if I subtract 1/2, I get 1/2, and then multiply by pi squared over 4, we get pi squared over 8. So what we have is this series identity that says if we do the sums of the reciprocals of the odd squares, we get pi squared over 8. Which is kind of cool. At least I think it's kind of cool. This is the kind of analysis that you need to do for that second problem on your homework. So I want to make sure we did one more like this. Okay. All right. Any questions on creating a Fourier series or making those identities for the Fourier series at all? Is that okay?
So when we're recreating it, we just switch out the part, the a sub n part to whatever works. Like in this case, we just got rid of any of the even terms.
Yeah, we just rewrote it so that we saved the odd terms. Exactly right. Yeah, so to save the odd terms, I need to replace my n with something that creates the sequence of odds. Yeah. It'd be the same thing if you were keeping the evens. You do the same idea. That's okay. Or do you want to see one more like this? Yes.
What is the pi in this like? Like, why does it go where it does in this equation?
What do you mean?
Like, why is it pi squared or why is it 4 pi? You know?
That's where it came from. This pi is coming out of the fact that we're integrating this thing with a pi on the inside. So if you think about the use substitution idea, a pi would come out in front. That's where it's coming from. All right. We can do another one. Sure, why not? All right, so doesn't matter. I'll make it go to 2. Let's do that one. Say we have f of x equals x from 0 to 2. What does that look like if you grab it? It goes and then right? Yeah, they call it the sawtooth wave. It goes up and then it goes up again and it goes up again, right? Okay. So again, if we want to find the Fourier series, reload this. Just to get rid of all that other stuff in there. All right. First thing we need to do is integrate this function from 0 to 2, but I think I can do that without actually typing it in. What's the integral going to be? 2, right? 1/2 base times height. So I'll get 2 for the integral. Then again, we'll divide that by the period, which in this case again is 2. So I'll get a 1 for the constant out in front when we're done. Right? Okay, cool. All right, so then we need to do our other integrals. Oops, not a of c. Well, integrate x times sine of n pi x. Again, where's the pi coming from on the inside there? Yeah, the period being 2. So we need to adjust on the inside with a constant to make the period be to match what we have. I don't care about the graph of that thing. Oops, I made those the A's. Those should have been the B's, shouldn't they? Yeah, see, I typed it in backwards. GeoGebra doesn't care. I'm going to leave it. GeoGebra real quick care if I try to change the name of it because it'll just make it. It'll just switch it on me anyway. So I'll do the other one. Let's integrate x cosine of n pi x. Any guesses on what this is going to be before I hit enter? Yeah, so that's not necessarily going to be 0 in this case because we get some nasty things. But let's see what we get. If I would have gone across down here and done this one, then I would have got 0, right? So it would have been odd. That one should have been 0. All right. There are the two pieces. So again, we could get the graph here like we did before. I just got to have my syntax is going to be flip-flopped. But let's see what the graph looks like just real quick. I don't really care about the graph part. I want to do the identity part. We said the constant here should be 1 because the integral was 2 to start with, right? There's no coefficient to put in front of the sum again. because the period is 2, half the period is 1, so we'd really just be dividing by a 1. I flip-flop my A's and my B's, so my A's here will be multiplied by the sine, because I wasn't paying attention, and my B's will get multiplied by my cosine. Ordinarily, I would have had my A's go with my cosine and my B's go with my sine. I just flipped it when I typed it in. Again, GeoGebra doesn't care if you can keep track of it. You can call it whatever you want. GeoGebra doesn't know what the standard notation is for these things, so you can use whatever you want. If you want to give it creative variable names, have at it. I don't care. There we go. Does that look like what you would expect it to look like? Again, notice that we did 10 terms here for this one. Doesn't look as good as the previous one that we did with 10 terms because again, we've got something that's not continuous, right? So it has a hard time trying to figure out what's going on with the discontinuity there. But if you do more terms, it'll get better in the middle, but it's still going to have issues near the boundary. All right. So again, let's see if we can write down what the Fourier series is without the sine and cosine pieces there in the coefficients. And then see if we can come up again with some other identities, or at least another identity. All right, so this one's a little bit easier to simplify than the previous ones. They don't have any alternating pieces going on because sine of 2n pi is always going to be 0. So in the A's, this is going to go away. Well, this is going to go away in the coefficients on the sines. This will go away in the coefficients on the cosines, right? Cosine of 2 pi n is always equal to 1, right? So if we want to write down the Fourier series here, we'll have, again, the constant term is still a 1. That's still out in front, right? Again, the way I have this written, I've got my A's, or I can go with my sine, and my B's go with my cosine. Let's do the B's first, just to keep it straight with what we typically do. This is always 1. This is 0. That's a minus 1. What do we get? 0, right? So there are no cosine pieces. So the part that we really have is just this. This is a 1. So we'll get a minus 2n pi over n squared pi squared. We can cancel an n and a pi. So all we get is a negative 2 over n pi sine of n pi x. So let me flip that over here so I can rewrite it over here. So again, your f of x here is 1 plus 1 to infinity, negative 2 over n pi sine of n pi x here. Okay. Smart's good? All right. So let's see what happens if we put in, say, 1/2 into the function. No, let's put in 1. Nope, I don't want to put in 1/2. Don't want to put in 1. What is f of a half? It's 1/2, right? Oops. I'll move out the negative 2 over pi out in front of the series. when we put in 1/2 for x, we get sine of n pi over 2 on the inside of the series there. And then I lost my n, didn't I? Right? I just plugged in 1/2 into x on both sides. The function is easy, right? The function is f of x equals x, so the added output is 1/2, so it has to equal the series on the other side. When I put in 1/2 for x, we get n pi over 2 on the inside. What does sine of n pi over 2 do as you change your n? Where does it go? It goes, what does it do? 1 to... That goes 1, 0, negative 1, 0, right? It doesn't quite alternate. It alternates every other term, and the other ones are zeros, correct? Sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1, sine of 4 pi, 2 pi is 0, and so on the line, right? Okay. Which terms survive then? Odds or evens? Odds, right? But the first term is going to be positive, isn't it? So we can replace this with an alternating piece of negative 1 to a power, but I need to make it, say, negative 1 to the n plus 1, so that the first term is positive and not negative, right? And then use a 2n minus 1 down there. Make things match. I could have also written this as a minus 1 rather than a plus 1. Doesn't matter. It'll still alternate the way we want it to. Now, if we solve for the series, we subtract 1 over, we get negative 1/2, right? If I subtract the 1 over, I'll get negative 1/2. Multiply by negative pi over 2, we'll get pi over 4. And I think we had come up with this one before as well. This is your alternating sum of the reciprocals of the odds. So it'll be pi over 4. So again, to get these power series, or not power series, these series identities using Fourier series, we need to simplify our coefficients first. To get a graph of it, like we were doing in GeoGebra, we don't really care to simplify the coefficients. But if we're actually going to do a power series identity, then we'll need to simplify. Is okay? Yeah, these are fun. I think these are fun. Any questions on doing these Fourier series stuff? All right, well, let's then switch gears to what we refer to as Monte Carlo simulations. So we're going to start this off by looking at, say, integrals that we would have a difficult time calculating. Let's just start there. And then we'll expand this notion going forward. So, for example, let's say you were asked to find the integral from, let's say, negative 1 to 1 of square root of 1 minus x squared dx. Well, if you remember your Calc 2, perhaps you remember your Calc 2, so you had me for Calc 2. But anyway, if I've got this difference of squares under a radical, and I can't use a U substitution to do it, what technique do we have to use? A trig substitution, right? So if I were to do this by hand and actually wanted to compute the integral by hand and find an exact value, I would need to do a trig substitution. In fact, just as a reminder, what would you let your x equal in the trig substitution? Sine of theta, right? You think let your x be sine of theta. The reason why you do that is because you get cosine squared underneath, and the square root cancel each other out, right? So anyway, I'm not going to do that. Let's do it another way. Let's do it geometrically, and so that we can actually get a value to compare our simulation to here in a second. Okay. What kind of a shape is this going to be if you look at y equals the square root of 1 minus x squared? What kind of shape are you going to get? If you do y equals square root of 1 minus x squared, how can you rewrite that? Yeah, it's going to be x squared plus y squared equals 1. Since I did the positive root, it's the top half of the circle, the semicircle, right? Yeah. The semicircle, half a circle. What's its radius? 1. So its area is going to be, the whole circle would have area pi, right? So this should be pi over 2, right? Should be half of pi. Okay. All right. So that was a little bit easier than trying to go through a U substitution idea to get to it, right? Or not a U substitution, trig substitution idea to get to it. We could have. But let's see if we can figure out this area in a slightly different fashion. All right, so, oops, I don't want to do that yet. All right, so notice that I could, let me just redraw the picture again. I could take this circle and I could put it inside of a rectangle. That semicircle is certainly inside that rectangle I just drew, right? I know what this area of this rectangle is. It has a height of 1 and a base of 2, so it has area 2, correct? So this semicircle takes up a certain percentage of the total area of that rectangle, right? So what we're going to do with this Monte Carlo simulation idea is to figure out a way to estimate what that percentage is, okay? And here's how we're going to do it. It's a pretty straightforward way to do it, actually. I'm going to take a bunch of random points in the rectangle. A bunch of random points. Pick how many you want, but just make them random points. Okay? If I want to get an estimate for the percent, if I know how many points I have, let's start there. If I want to get an estimate for the percentage of the area that the semicircle takes up, how might I get an estimate for the percentage of the area the semicircle takes up using the points? Yeah, exactly right. Take how many points are inside the semicircle, and divide by how many points there are. That'll give you an idea of the percentage of the area taken up by the semicircle. Multiply that by the area of the rectangle, we now get an estimate for the area. Okay. That's the idea behind doing Monte Carlo simulation, at least for integrals goes. Okay. So let's see if we can do that. Let's do it with Excel first, because this, I don't know why I just took my keyboard off. I want the keyboard on. Okay. All right, so let's go over to Excel so I can teach you a couple other functions here. All right, so let's say to start with, we want to do, I don't know, pick a number of points, a lot of points. How about 1,000? Okay, let's do 1,000, okay? Why not? Excel will do a whole load of rows. But let's say I want to do 1,000 points. So here's how I can make 1,000 points quickly in Excel. So I'm going to use the function that creates a random array. Now notice that the x values that we want to pick, the x values we want to pick are in a different interval than the y values we want to pick, right? So I'm going to create two separate arrays, one for the x's and one for the y's. If they both came, say both of them were between -1 and 1, I could use this one command. And I'll show you how to do that here in a second. Okay. But right now I'm going to use this random array command to create x's and this random array command to create y's. Okay. So notice that it asks you for number of rows that you want and number of columns that you want. So if I want to create 1,000 x values, I'm going to make my rows be 1,000. And then I'll just make my columns be 1 because I'm just going to make it one long column of x's. Okay. If you'd rather it be horizontal, you could do 1 row and 1,000 columns. I just think that's ugly, personally. You can do it either way, right? I'm just trying to create a list of x's. Whichever way you want to do it, I like to think about them vertically, but if you want to do it horizontally, have at it. I don't care. All right. Then, if you just ended it here, and you just put a parenthesis at the end of this, the defaults for the min and the max are 0 and 1. So it would give you 1,000 random numbers random numbers between 0 and 1. Okay. But we don't want the numbers to be between 0 and 1. We want the numbers to be between -1 and 1, right? So we can put those bounds in here as -1 and 1. You also have the option that if you want to create integers rather than decimals, you can. That's not going to help us here. So I'm going to end the parenthesis. The default is that it creates decimals. If you want to make it random integers in a range, then you would write true there, and then it would create random integers. If I hit enter, I get 1,000 values. Again, Excel will recalculate random numbers anytime you do a new calculation. So I'm going to type in the next command here for the b's to get the y coordinates. Notice that the first column will change when we hit enter. Okay. So again, the command here is random array. We want 1,000. I want them to match. I want 1,000 rows in one column. This one, we do want the y's to be between 0 and 1. So I don't need to type in 0 and 1. You can, it doesn't hurt, but I don't need to. The default is 0 to 1. Okay? Notice the first column change. Every time Excel does a new calculation, it recalculates the random. Okay? All right. We want to check whether these points fall within the semicircle, right? So we need to check if the y's are less than or equal to the square root of 1 minus the x's squared, right? Agreed? Okay. So there is a COUNTIF command in Excel. Oh, well, I need a range and a criteria here, so I should be able to see if it'll do it all at once. Last time I was doing this I did it with just a, let's see if it'll work. I didn't try it this way before. All right, so there's my range, right? Since we did 1,000 points, and I'm in columns A and B, my upper left-hand corner of my range is A1. My lower right should be B1000. Right? Okay. The condition is that we want, I can write it as the second coordinate is less than or equal to the square root of 1 minus the first coordinate squared, or I can just check that they're inside the unit circle, right? So I could do this as a1 squared plus b1. I can't do it that way. Never mind. We need to do an intermediate step. I was thinking I could be clever, but I don't think I can do it that way. Let's do an intermediate step. I lied. Sorry. I didn't do it that way in my office because I don't think it'll work. If somebody can figure out how to make it work that way, I'd be interested to know, but I don't think it'll work. Here's what I'm going to do instead. I'm going to check to see if like we said, the second coordinate is less than or equal to the square root of 1 minus the first coordinate squared, or if the point is in the unit circle. So if a1 squared plus b1 squared is less than or equal to 1, that's inside the unit circle, right? Then that's a good value. I'll call it 1. Otherwise, I'll make it 0. I'm just creating a way here to check whether or not a point is in the unit circle and then count how many there are. I will go back and use that countif command. I just don't think I can use it the way I was using it. I might be able. There might be a way to do it, but I don't know how to do it off the top of my head. I have to investigate. But this will work. This will just check to see if we're in the unit circle. So it'll spit out a 1 if it is and a 0 if it's not. And we will count how many 1s there are. Right? That's the idea. Okay. So I need to copy this all the way down. At least the shortcut method for me to copy it all the way down is I'm going to hit Control-C to copy the cell. And then if you hold Control-Shift and then the End key, it'll pop all the way down to the bottom, so you don't have to scroll. Okay, I'll tell you again here. Hold on. Now I have to go back on the top. Yep. So Control-C does copy, right? Scroll down one cell. Just go down one cell. The keystrokes all at the same time. Well, I do it in order, but hold all keys down. Control-Shift-End will take you all the way to the bottom of that column. And then just hit Enter and it'll copy everything down. Oh, darn it. All right, so like Matt said earlier, one of the things that we want to do is count the number of the points that are in the unit circle and then divide by the total number of points, right? So this countif command will count the number of 1s that we have. And then we can divide that by 1,000, and that'll give us our percentage that's in the unit circle. So our range here in this case is C1 to C1000. And I want to know how many 1s we have. There are 764 of them, right? That tells us how many there are. So again, the percentage of points would be that number divided by 1,000. That's how many points we have, right? Yeah. Okay. And then we said we would need to multiply this by the total area to get the estimate for our integral, which gives us 1.552. We said that the exact value should have been pi over 2. Here's your pi over 2, right? So if I just keep doing different simulations here. I did copy and then paste and then just running it over and over again. Notice that one's a little bit bigger. That one's a little bit smaller. That one's significantly smaller. That one's bigger. That one's smaller. That one's smaller. That one's bigger. smaller. We are doing a bunch of simulations here to get estimates of what it is. Yeah, Natalie?
What was in the
I multiplied it by 2. E1 times 2. I would have actually would probably done this all at the same time. I was just divided by how many points we had and then multiplied by 2. But I was just trying to illustrate. This counts how many are actually in the unit circle. This is the percentage that is in the unit circle versus the rectangle, and then that times the total area of the rectangle. So again, all we're doing in that command is counting how many ones we have in column C. So I'm using that if command to, pardon me, I'm using that if command to determine whether or not the point meets the criteria that I want it to. Then we calculated the percentage of points that had that criteria, multiplied by the total area to get us an estimate for the integral. You can probably imagine coding this stuff up too, right? Yeah, Sean. Yep. All right. So let's say you wanted to do something that was a little bit more challenging, perhaps. Because that one we could have actually done by hand. So maybe you would have wanted to know, let's say we want to do the integral from, let's say 0 to 2 of square root of 1 plus x cubed dx. All right, so same concept. This one, I mean, you could type this into something else and get an estimate for the integral using other techniques. But we want to illustrate the simulation idea. Same concept, except that this one we can't do by hand. This integral is impossible to do by hand. Don't bother trying. You can't do it by hand. Okay? So the only thing we can do is estimate this integral. Okay? All right, so let's think about, by the way, you get, if you remember doing arc length stuff in Calc 2, the problems that you could actually do by hand were all rigged because you can get a lot of integrals that look like this in a hurry, and you just can't do them by hand. Or don't want to do them by hand, one or the other. All right, so same concept here. I want to think about what this function looks like and then build a bounding rectangle around it, okay? Well, notice as x gets bigger, certainly this function gets bigger. So the biggest this function ever gets is at the right endpoint, which is what, 3? Right? So we can bound this thing. I'm not going to worry about what a graph looks like necessarily, but it certainly starts here at 1, doesn't it? When I put in 0, I get 1. When I put in 2, we get 3. So this function goes here, and it must curve slightly that way because it kind of looks like x to the 3 halves. So it has to be a little bit, it's not a line, it has to bend a little bit, right? So the area we're looking for is this area, right? I want a rectangle around the area, and I'm using a rectangle because rectangles are easy to calculate the areas, right? It's kind of how you did integration to start with, right? When you're finding area under a curve, you used rectangles because those were easy areas to calculate, right? Same kind of concept here, except I'm going to take a big rectangle. How high do you think you want your rectangle to go? 3 because that's the highest the function goes, right? You could go bigger than 3 if you want to and be sure that you've had the whole function underneath it. But of course, the bigger you get, the less accurate you're going to be because, again, we're picking random points, right? So I would like this to be as close to the function as I can, right? Bottom number, 0, right? I mean, if you want to be clever, you could cut it off at 1 and then just add 2 to the area at the end, right? Because I know that for a fact is inside the rectangle and the function. So if you wanted to try to squeeze it a little bit, you can. Okay. But let's just take a big bounding box around it. We'll go from 0 to 3. Okay. All right. So again, if I go back over to Excel here, I'm just going to open up a new sheet. I want to create, since I've got points in the plane here, I need to create points, X's and Y coordinates. So again, let's do it with 1,000 points. Nothing special about 1,000 except that nice round number, I suppose. Use that random array command. 1,000 rows in one column. That'll give me 1,000 X's. Smallest X we want to use is, and the largest X we want to use is 2. Good. That creates 1,000 X's. Now I also want to create 1,000 Y's. Smallest Y we want is 0. Largest Y we want is 3. Yep. We're just building a bounding box around the whole area. You could also do this for double integrals and build bounding cubes around things. Bounding literally boxes around things. Okay. We'll do an example of that later here. Yeah? We okay with creating the points? Again, nothing special about 1,000. You can make it 3,000 or 20,000 or what have you. All right. Next thing we want to do is create that if command. All right. We want to count the number of points where the y coordinate is less than the square root of 1 plus the x coordinate cubed. Right? So the y coordinate we're using is the b's, right? We want that less than or equal to the square root of 1 plus the x coordinate cubed. So that would be the syntax for that. Y is less than or equal to square root of 1 plus x cubed. If that condition is met, what do we want to use? A 1. Actually, it literally doesn't matter. You can make it whatever you want, as long as you're counting for that particular instance, right? And then otherwise, we'll make it a 0. Really, you just need 2 different things here so that I can count the one that I want. Doesn't matter if it's a 1 or a 0. Usually think about it as a 1 or a 0, because if you think about it from a computer perspective, 1 would be true and 0 would be false. That's why I use 1 and 0, but literally the conditions don't matter as long as you can search for them. So far, so good? Again, now we need to copy that all the way down. Control C on the cell. Scroll down the one spot, arrow down the one spot. Control Shift End highlights all of those. And then hit Enter. And it puts that whole, it compares them all the way down. And now we'll use that count if command to count the number of ones, right? So the range is C1 to C1000. That second number, of course, will change if you've got a different number of points, right? If you got 10,000 points, you'd go down to C10,000 as opposed to C1000. Okay. We want to count how many ones we have, right? 555 ones, it says. and that's in that round. We want to divide the number of those by how many points. You could do this all in one cell. I'm just doing it step by step so you can see the process that we're doing, right? Divided by the number of points. So again, that denominator will change depending on how many points you have, right? That tells you the percentage of points that that are in the rectangle and land under the curve, right? So then to find the definite integral, we'll take that percentage and multiply it by the area of the rectangle, which in this case is 6. So 2 by 3. So you take the percentage of points that are under the curve, multiply by the total area, and we get 3.18 in that case. And again, if you wanted to, in Excel, if you wanted to run it over and over again, anytime that Excel does a new calculation or a new command, it will just recalculate all the randoms, right? So if I hit Control C and then just start pasting, Control V, I get a whole bunch of values. So you can, this is basically doing simulation over and over again. If you want to see it change the different numbers. What we notice is that it's around, looks like 3.2-ish. Again, if you're doing computer programming, it'd be a little easier because you could do this over and over again, keep track of it, right? And then do the average at the end. You could run statistics about you could make a histogram based on what the different answers you're getting. There's all sorts of things you could do from a simulation standpoint, right? We should be able to check this against what the actual value is. So if I go over to GeoGebra and do the integral, the function is square root of 1 plus x cubed, and I want to integrate that from, what did I say, 0 to 2? It said question mark because it's trying to do it symbolically and can't. Okay, so let me switch views. If I go and just tell it to do it in an algebra window, it should tell me the actual value. There you go. You get about 3.24, which is about what we got, wasn't it? So it gave me a 2 decimal approximation of 3.24. And again, if I change this over and over again, I get some that are lower, some that are bigger, right? Which you would expect, right? Because we're picking random numbers and counting how many are in there. If we use 4 points, probably get a little bit closer. But this is how the simulation works. We're just generating some random points and then checking a condition being met. That's okay? So maybe you wanted to do, rather than a single integral, maybe you wanted to do a double integral. Say we wanted to look at the iterated integral 0 to, whoops. I need 2 differentials here on the end. Say we did the iterated integral 0 to 1 and x squared to x, and we wanted to integrate the function xy with respect to y and then with respect to x. So now we have a surface in 3 dimensions rather than a graph in 2 dimensions, right? And we're looking for volume under a surface rather than area under a curve. But it's the same kind of concept, right? I think of my z coordinate being a function of my x and y. So I'll pick some x's, pick some y's, pick some z's as well. Calculate random points in a box that contains the volume that I'm interested in and do the exact same process. See if it's in my region that I'm interested in and underneath my surface, right? Yeah? Okay. So this one's a little bit more involved because I need to make sure that I also have it in between those particular values. So, for example, if I wanted to make sure that I actually had 1,000 points in my region here, then I would have to be a little bit more careful. But let's just worry about what we're doing. So let's say we've got this particular function. Your x's are going from 0 to 1. Your y's are also going to be in between 0 and 1. They just also have to be between the x squared and the square root of x, right? Notice again, as x gets bigger and y gets bigger, the z value will get bigger. So your z value also has to be between 0 and 1, right? Agreed? Okay. So what we're going to do is same idea. Oops. Let me get out of that so I can zoom in so you can see what I'm typing. Let's start with, I'll start with 1,000 points, fine. Doesn't matter. I'll start with 1,000 points. In this case, though, since my x's, my y's, and my z's are all between 0 and 1, I might as well create them all at the same time. Right? I don't need to do it individually because it's the same interval. So I'm just going to tell it to make 1,000 rows and 3 columns in this case. And the defaults are 0 to 1. So I don't even need to type that in the max. Okay? Boom. There we go. I just created 1,000 points in the unit box in 3-dimensional space. That was pretty fast. Right? Okay. All right. In this case, however, we need 2 conditions to be met. Right? Not only does it need to make sure that we're counting points that are below the surface, I also need to make sure that my y coordinates are in the right spot. Don't I? Yeah. Okay. So the way we would do that in this case is we're going to use the AND command in Excel. I have 2 conditions that have to be met, and both of them have to be met in order to count them correctly. Right? So the first one is that I need my second coordinate to be bigger than or equal to the first coordinate squared. Right? And actually, in Excel, I'm going to type it in 3 conditions. I also need my second coordinate to be less than or equal to the square root of the first coordinate. Right? This makes sure that I'm above x squared. This makes sure that I'm below the square root of x, right? In between those 2. And then the third condition we need is that the third coordinate is less than or equal to the product of the x and the y. So again, the first 2 commands are making sure that you're in this interval for your y's. The last command is making sure that you're counting the right thing underneath the surface, right? Just like we did underneath the function for area. Okay. And then we'll end off this if command just like we did the other one. If the conditions are all met, we'll make a 1. Otherwise, we'll make a 0. Same concept, okay? Copy that down. There's one that met the criteria. Not very many here. There's a couple more, right? Not a lot meeting this criteria. Okay. We'll use that count if command to count how many. Only 93 out of 1,000 meet those criteria. In this case, so I got 8.4% of them are in there. So then we would multiply that by the volume of the box that we used to bound. What is the volume of the box we used to bound? 1. So 0.084 is about the volume is what it says, is that what that value should be? Okay. Yeah, definitely.
Can I see what you have in D again?
So again, in D, we've got those conditions. The y value has to be above x squared and below the square root of x, and then the z values need to be less than the product of x and y. All right, we'll do more of these next time. And like I said, we'll also get your last major assignment assigned. Have a good one. We'll see you on Thursday.